This video is about implicit differentiation. For our notes, we're going to start with more of a conceptual discussion to kind of get into this. First of all, a question: is x times y equals 1 a function? Now that hopefully starts to cause you to sift through your mind about the definition of a function and what that means. And the answer is not supposed to be super clear with this question. That's kind of the point. And this will help us understand two things. We have what's called explicit form. And in that way, you could make this into something that's more familiar with the function language, but typically we would solve for y to do it. So we would say, oh, if I just divided both sides of this original xy equals 1 by x, I would have y equals 1 over x. And then you could say, in this case, is what we're used to in algebra, that y is a function of x. But that's an explicit form of the function because y is alone, and you have x's on the other side of the equation. That's the explicit form. Now, the implicit form, but that's the original xy equals 1. So because we could write it explicitly as y equals 1 over x, and in that way say y is a function of x, we could say that this xy equals 1, the same thing in a different form, is really an implicit function. In other words, it's implying that y could be written as a function of x, but it's not shown explicitly in this form. Well, it turns out many equations only have an implicit form. So this is not an example of them, or one of them. This one could be written either way, but I just wanted to use it to show you the two different forms. If you had some other function, for example, we could say something like x cubed plus y cubed equals 6xy. Now, if I gave you that and said, okay, there, it's an implicit function, can you put it in an explicit form? You wouldn't be able to. There's no way to solve for y, where y is alone, and the other side only has x's. And so you cannot put it in explicit form, which may beg the question, well then, how would I take the derivative of a equation like this? Well, that's why we need what's called implicit differentiation. Sometimes we have to take the derivative of an implicit function. So let's recall, first of all, to use the chain rule and find something very familiar. If I wanted the derivative of 2x plus 1 in parentheses all to the 5th power, then the chain rule that we know already would say, see this as a composite function where the outer function derivative happens first. That's why we would take this 5 and throw it down in front to make this 5 times the inner function 2x plus 1. But then we would decrease and make that now to the 4th power. But then, don't forget, this chain rule says then you have to take the derivative of that inner function and multiply by it at the end. Of course, the derivative of 2x plus 1 is just 2, so we have to multiply by that extra 2 at the end, which means altogether, we'd simplify this and say it's really 10 times 2x plus 1 all to the 4th. Okay, so that's chain rule derivatives, which we've done by now. That's not the point of this lesson. But if you understand the chain rule well enough, you can see that implicit differentiation is really just the chain rule. It just looks strange until you see it as that. So now let's assume y, the variable y, represents some function of x. So when I want to take the derivative of y to the 5th, we're going to pretend that y, this variable y, is hiding something. Okay, it's kind of covering up some cluster or function of x's. If that was the case, then that's actually exactly what we just did in this example. Right? So I want to take the derivative of it. I would use the chain rule and see y, the inner function, as some hidden function of x, where the outer function is this 5th power. And I would write the 5th power down in front. I would copy the inner function, which remember we're saying is just y here, and then I would decrease the power of it by 1. So now it's to the 4th power. So I have 5y to the 4th. But then, don't forget, we would take the inner function and multiply by its derivative. Now, the thing with an example like this is we don't know what that inner function is. Remember, y is just hiding some inner function of x. So instead of writing out what it would actually be, we're simply going to write it as dy dx, which represents the derivative of whatever it is. So in that way, we'll say the derivative with respect to x, d over dx, of y to the fifth is really 5y to the fourth times dy dx. If we go back up to the example we just did, the derivative of 2x plus 1 to the fifth, I think it'll help kind of match things up to color coordinate here. So the 2x plus 1 that we had in the previous example, that's like the y in this implicit form. So it was 2x plus 1 to the fifth, now it's y to the fifth in this implicit form. When we took the derivative of it, in the first example, we ended up with 5 down in front times 2x plus 1 to the fourth times 2. Well, again, now in this implicit example, we have 5 times y to the fourth. So again, there's the y representing the 2x plus 1. And then, since the previous example had the function defined explicitly, its derivative was also explicit, right? We took the derivative of the 2x plus 1 inner function, and that turned out to be a 2. Well, this time, we don't know what that inner function is. Remember, the y is kind of like masking it or covering it up, but the derivative of it now is just this dy dx in the same way. So I think if you kind of match these two examples up, you get a pretty good idea of how implicit differentiation works. Let's try an example where we want to differentiate, but we're going to have to use implicit differentiation to do it because we're given implicit expressions or functions, you could say. So the first example is x cubed plus y cubed equals 6xy. Now, if you look above in our notes, you'll recognize this is one function we wrote down as an example of an implicit function that cannot be solved for y. You cannot get y alone with only x's on the other side of it to write this explicitly, which means none of the explicit derivative rules work, which is why we want to use implicit differentiation. To get the process started, I think a good way to do it is to take the derivative with respect to x. So we're going to say d over dx. We're going to apply that to both sides of this original function. So I'm going to say d over dx of the left side, which I'll just copy down as x cubed plus y cubed in parentheses. And I'm going to say that equals, and now I take the same derivative, d over dx, of the right side, which was the 6xy. Now, any particular term we take the derivative of that's already written explicitly is just going to use all of the derivative rules we already have. So on the left side, when we see d dx of x cubed, that could be written as 3x squared, which is just using the power rule for derivative. That's an explicit function of x, so we simply use the power rule for that. But then we move on to the next term. If you want the derivative of y cubed, this is where all of a sudden now we want d over dx of y cubed. The mismatch in variables there should give you a hint that we have to assume that y is an implicit function of x. It's hiding some kind of x's or something, in which case we would use the power rule like we just did above. In our rule, we'll put the 3 down in front and write this as 3y squared. But then, using the chain rule as we would have to here, we'd multiply by the derivative of y. Remember, we don't know what y is representing. We assume it's a function of x, and so we'd write it as just dy over dx. Or some authors will just use a y prime there instead of dy dx. I like the dy over dx though, but it means the same thing as y prime. Now on the right side, we'll continue in the same way, but notice we have the derivative with respect to x of a function that includes x and y. So we have to consider this an implicit function which has two pieces, the 6x being the first and the y being the second, with those being multiplied together, or you could say that being a product rule. This is easy to forget when doing implicit differentiation. So here we go with the product rule, where we say first, which is just 6x, times derivative of the second. Now the second is y, so its derivative is dy dx. We don't know what y is hiding, so we assume it's some function of x whose derivative is dy dx. There's first, derivative of second, plus second, now we can write just the y for the second, times the derivative of the first. Well, the first is this 6x, in which case you could write it as just 6 for its derivative. There's a couple different ways to write that. You could have maybe thrown the 6 out in front of the derivative as well, but the main idea is that this is the product rule happening within this implicit differentiation. There's first d second plus second d first. Now, how do you finish a problem like this is a fair question. Well, if we wanted to find the derivative of this original function, then really dy over dx represents that derivative, which means now after going through and applying all the implicit differentiation, we now want to solve for dy dx. Now, if I understand which terms have the dy dx factors, I could get those on one side, making this then 3y squared dy dx. That term was already on the left side, but I want to bring the term on the right side that had the dy dx over with it, which would be plus. Actually, if I bring it over, it'll be subtracting it. So I'd have a minus 6x dy dx. And then anything else I had, I want on the right side. So I already had this 6y over there, but now I'd be subtracting this 3x squared from the original left side, which did not have a dy dx term. Okay, so now we've isolated things where the dy dx is on the left side, everything else is on the right side. At this point, you just want to factor out the dy dx on the left side, which will leave us with a 3y squared minus 6x. That's equal to 6y minus 3x squared on the right side. And then your answer is going to be dy dx alone, which you could do just by dividing by this 3y squared minus 6x factor on both sides. So we'd end up with dy over dx equals, on the right side I keep the 6y minus 3x squared as the numerator, but now I'd be dividing it by this 3y squared minus 6x to get finally dy dx alone. This is an implicit derivative coming from an implicit function. So notice the derivative doesn't have only x's on the right side of it. It has an x and a y here and there. But nonetheless, it operates just like a derivative. Let's try a second example. This one reads x times e to the y power equals x minus y. Well, obviously, y is not alone with all the x's on the other side of it, which means this is an implicit function, which means we'll apply implicit differentiation. If I take the derivative with respect to x, d over dx, of the left side, which is x times e to the y, and I set that equal to the derivative with respect to x, d over dx, of the right side, which is simply x minus y, and then apply the derivative rules as we know them, assuming y is some function of x that will need the chain rule as we've been doing here. Then on the left side, I have this x times e to the y. For that, I'm really going to need the product rule because that's a product of two functions, which means I have first x times derivative of the second. Now, the second is e to the y. We assume that's an implicit function, so we'll say e to the y times the derivative of its inner part, the derivative, the exponent y, which would just be the dy over dx. So there's first d second, that's x times e to the y times dy dx on the left side, plus second, which is e to the y, times derivative of the first, which is just the 1. Okay, so that's the left side. Moving over to the right side, we take the derivative of each term. Well, the derivative of x would just be 1. That's an explicit function of x. We use just the regular derivative rule for that. Derivative of x is 1. And then we say minus. Now the derivative of y is dy dx. You don't have to force the power rule on that, but you could. If you saw that as y to the 1, then you could use the power rule like we've been doing in other cases, and it would work just the same way. But dy over dx would be that derivative for that term. Now, remember, the goal is to get dy dx alone. We have a couple of them here, which means we want to solve for them. If I take the left side and move all the dx, all the dy over dx terms to it, then I'm going to keep this x e to the y dy over dx over there. But then I'm going to actually add the dy over dx term that we had on the right side over to it now, so plus dy over dx. And then I'm going to bring everything else to the other side. I already had a 1 over there, but now I want to subtract this e to the y term that I had on the left side. We're trying to get all the dy dx's on one side, everything else on the other, so that we can factor out dy over dx in this next step, which would leave us with x e to the y plus 1 equals this 1 minus e to the y. That's the right side. And then if I isolate the dy over dx by dividing by this x e to the y plus 1 on both sides, I'll end up with finally 1 minus e to the y all over x e to the y plus 1. It's not going to get much better than that. We would call that the implicit form for this derivative. Let's try a third example where this time we want to find an equation of the line tangent to the following implicit equation. Now notice this is a slightly different scenario than we've been doing here just recently. We want to find the equation of the tangent line. Now we've done that before and it involves a derivative, but now we're doing it with an implicit function. So let's go ahead and let's take this in two steps. First, find the derivative in implicit form, and then we want to find the slope of the line tangent to it at the point 0, 0. We'll kind of call that like phase 2 of this problem. All right, the equation reads cosine of x times y equals 1 plus sine of y. Now, I want the derivative of each side of this function first. So we'll say d over dx of the left side, which is the cosine of xy, equals d over dx of the right side, which is the 1 plus sine of y. Now, let's apply our implicit differentiation to this. On the left side, we have really a composite function. We have cosine of xy. Well, the outer function is cosine. So to do the chain rule, we start with the derivative of the outer function. The derivative of cosine is negative sine, and then keep the inner function. So we have negative sine of xy, but then we have to multiply by the derivative of that inner function. So that inner function being xy is a product. So we're going to multiply it by, here we go, first, which is x, times d second, which is dy dx. The derivative of y with respect to x. There's first d second plus second, which is just the y, times the derivative of the first, which is just 1. Okay, there's a little product rule going on for us within this implicit differentiation here. Be careful of that. It's easy to miss that step. That's the left side. Now on the right side, we're going to go term by term on this. The derivative of 1 would be 0. And then we'll say plus the derivative of the second term. Okay, again, here's a composite function, sine of y. Remember, y is hiding some function of x. So the outer function, sine, has a derivative which is just cosine of, keep the inner function y alone, but then multiplied by the derivative of the inner function, which would be the dy dx. Let's try to continue and clean this up a little bit better. If I distribute this negative sine of xy into the brackets here on our left side, I'll end up with negative x sine of xy dy dx. That's just going into this first term here. And then going into the next one, which is just a y, I'll have minus y sine of xy. And then on the right side, the 0 is gone, so I really just have this cosine of y dy dx. Now remember, the goal is to get dy dx alone, and we could do that by just shuffling the terms here a little bit to get them on the same side first. So this would mean negative x sine of xy dy dx. That's already on the left side. If I bring this other dy dx term over there, I'll subtract and have minus cosine of y dy dx. And then I'm going to bring the other term that doesn't have a dy dx to the other side, so I'll add, and on the right side then just have a y sine of xy. At this point I can factor out the dy dx, which would leave me on the left side with this negative x sine of xy minus cosine of y. And on the right side I just have this y sine of xy. If we now get the dy dx alone, we'll end up with dy dx on the left side, and I divide everything else on both sides to get, I already had a y sine of xy on the right side, but I will be now dividing that by everything I had multiplied with the dy dx in the previous step. So that's a minus x sine of xy minus cosine of y. Okay, so this is like phase one of our answer in this problem. This is dy dx, which we just found using implicit differentiation. But now they want to know, how about at the point 0, 0, we want to find the equation of the line tangent. Well, as you know, in point-slope form, that'd be like saying, you know, y minus y1 equals m times x minus x1. We've done this even recently with derivatives. The derivative is the slope. That's what the m is. We can find that at 0, 0 by simply plugging in those values for x and y in our derivative, which cleans it up pretty quickly actually. So we'll now say dy dx, this is now at the point with 0, 0, is 0 times the sine of 0 over negative 0 minus the cosine of 0. I'm just plugging in 0 for x and y in our dy dx derivative that we just found. Of course, this turns out to be 0 over negative 1, which is really just 0. So if our slope is 0, we could go back and try to plug that in, but that means y minus y1, which is 0 from the point we had, equals m, which is 0 times, well, whatever else is going to be 0. So this just simply means y equals 0, which you may recall is a horizontal line. In fact, it's right on the x-axis. That must be the equation of the line that's tangent to this curve at that point.